We now move to the final part of the talk. The goal is to show how point processes provide a common language for exceedances, rare events, and clusters of extremes. In this last section, we look at the object that sits behind exceedance counts, point processes. The basic idea is simple. If we observe a sequence of points in a measurable space, we can count how many of them fall in any region of interest. This counting rule defines a counting measure, and a random counting measure is what we call a point process. This framework is especially useful in extreme value theory because exceedances above a high threshold are naturally represented as points. The first example on the slide records only the times at which the observations exceed a high threshold. The second example records both the time of exceedance and the normalized magnitude of the observation. In this way, point processes allow us to study not only how often extreme events occur, but also when they occur and how large they are. To study a point process, one possibility is to look at its finite dimensional distributions. This means looking at the joint distribution of the numbers of points falling in several regions. This is intuitive, but in practice, it can become cumbersome. A more convenient tool is the Laplace functional. The formula displayed on the slide says that we test the point process against a non-negative function and then take an exponential transform. Since a point measure is a sum over observed points, this integral is simply a weighted sum over the points of the process. The important message is the last one. Weak convergence of point processes can be checked through the convergence of Laplace functionals. This is why the Laplace functional plays the same role for point processes as characteristic functions play in classical probability. The first reference model is the Poisson point process. It is defined by two properties. First, the number of points in a given set follows a Poisson distribution, with a mean given by the mean measure of the set. Second, counts in disjoint sets are independent. The displayed expression gives the Laplace functional of a Poisson point process. I will not read the formula, but its structure is important. It depends only on the mean measure and on the test function. This makes the Poisson process analytically tractable. For extreme values, the intuition is very clear. High threshold exceedances are rare events. When the observations are independent, these rare events occur almost independently. This is why exceedance point processes often converge to Poisson point processes. The Poisson point process is appropriate when extreme events occur in isolation. However, in dependent time series, extremes often appear in clusters. For instance, a heat wave lasts several days, financial turbulence may persist over several trading days, and a storm may generate several high observations over nearby locations or times. This motivates compound Poisson point processes. The cluster centers occur according to a Poisson mechanism, but each center generates a random number of points. The distribution of this cluster size is denoted by the symbol shown on the slide. The displayed Laplace functional is the clustered analog of the Poisson formula. The main extreme value message is the last sentence. Under dependence, the limiting process of exceedances is typically compound Poisson rather than Poisson. This is the mathematical way to capture temporal clustering of extremes. This slide states the convergence framework. Weak convergence of point processes means that, for suitable sets, the vector of counts in these sets converges in distribution. Equivalently, and often more conveniently, we can check convergence through the Laplace functionals introduced earlier. The last part gives the classical independent exceedance limit. We choose the threshold so that the expected number of exceedances converges to a finite value. Under this normalization, the exceedance point process converges to a homogeneous Poisson point process on the unit time interval. This result is the point process version of the law of small numbers. It also explains why the Poisson approximation is so central in extreme value theory. It is the natural limit of rare exceedance events under independence. The dependent case requires an additional condition. The mixing type condition displayed at the top of the slide is designed to ensure that exceedance events far apart in time are approximately independent. The formula defines a dependence coefficient between exceedance events in two separated blocks. The condition requires this coefficient to vanish when the separation grows, but not too fast relative to the sample size. Under this condition, and under the same high threshold calibration as before, any limiting exceedance process must be a homogeneous compound Poisson process. The intensity is reduced by the extremal index, which lies between 0 and 1. This index measures the loss of independence caused by clustering. The final identity gives an important interpretation. The reciprocal of the extremal index is the expected cluster size. Therefore, a small extremal index means large clusters, whereas an extremal index close to 1 corresponds to nearly isolated extremes. Let me now connect this point process viewpoint with generative modeling. A generator for extremes should reproduce several extreme value features, not only the bulk of the distribution. First, in the univariate case, it should reproduce the tail index, the GEV or GPD parameters, and high quantiles. These are the basic quantities that control extrapolation beyond the observed range. Second, in the multivariate case, it should reproduce tail dependence functions, extremal coefficients, and the distinction between asymptotic dependence and asymptotic independence. These quantities determine whether extreme risks occur jointly or separately. Third, in time and space, it should reproduce the extremal index, the spectral tail process, and the cluster size distribution. These are the objects that describe the dynamics and geometry of extreme episodes. A practical workflow is therefore to fit the univariate EVT structure first, and then train or regularize the generator so that it respects these tail features. EVT acts as a specification layer for generative models. Thank you very much for your attention. I would be happy to take questions, especially on the link between EVT constraints and generative modeling. This slide gives a short list of references for further reading. Berlant and co-authors, Coles, Embrechts and co-authors. De Haan and Ferreira and Resnick are standard references for the foundations of extreme value theory and heavy tails. For more recent developments, the handbook by De Carvalho, Husser, Navo, and Reich provides a modern view of statistics of extremes. The books by Kulik and Solier and by Mikosch and Winterberger are particularly useful for heavy-tailed and extreme value time series. These references cover the main tools discussed in the talk: univariate limits, multivariate extremes, max stable processes, generalized Pareto models, and point processes. This backup slide summarizes the main vocabulary used throughout the talk. GAV distributions are the limit laws for normalized maxima, whereas GPD distributions describe threshold exceedances. Regular variation is the standard mathematical formulation of power law tails, and it is associated with the tail index. Max stability is the stability property behind maxima. Threshold stability is the corresponding property behind exceedances. These ideas extend from the univariate setting to multivariate vectors and to stochastic processes. Finally, spectral measures and spectral functions describe the angular or shape component of an extreme event. They separate severity from dependent structure, which is essential for simulation, interpretation, and diagnostics of extreme episodes.